All right, this is 8.2, estimating a population proportion. We're actually going to create full-on confidence intervals today. So for people that come to class, we're going to do this activity. And what I want you to do is, if you really want to go out and buy 50 Hershey's Kisses and then just toss them and count in your sample of 50 how many land flat. If not, I want you to use this point estimate in number 1 that you see I wrote right here. So once you have number 1, I want you to work on 2 through 8. So I highly suggest you pause this video, work on 2 through 8, and then obviously start it again just to make sure that you did everything correctly. So I'm going to talk about this. So again, I think you'll remember this more and feel better about it if you actually try it yourself. I'm making people in class, so go ahead and make yourself pause this and actually try 2 through 8. All right, welcome back. So the population who do I want to know information about? I want to know information about, if I throw a kiss, what's the probability that it lands flat? So I want to know about all Hershey's Kisses. And P is what I want to know, my true proportion that land flat. Well, I don't have access to all the Hershey's Kisses to toss them and count how many land flat out of the total amount that there are in the world. So I can't do that for the whole population. So I got a sample of 50, and my statistic is 0.42. So now, to try to find the true P, I'm going to build a confidence interval. In order to do that, 3 through 7 leads you through the 3 conditions that must be met in order to build a confidence interval. And you have to prove that these conditions are met before you actually build it. So number 3 talks about random sampling. That's the first condition you have to prove. You just have to prove that you either sampled randomly, or you'll read through the context of the question on the AP test and say, yeah, they said they sampled randomly. 4, we're going to need variability of our samples in order to create this confidence interval, because we need to know how spread out our samples could potentially be that we collect, and where ours fits in. The sampling distribution will help us, the variability of that, the standard deviation, will help us know where that fits in with the others. But if you remember, in order to do that, we need to prove that we sampled without replacement, or that it's okay that we didn't. So the 10% rule in number 5, 10% condition, helps us know that, okay, we're good to go with our variability. And then 6, because we don't have a true P hat, because we don't have a true P, we're going to use a P hat instead. So we don't have a true standard deviation of the sampling distribution, but we do have an estimate, and this is our standard error. 7 is condition 3. So when we get our sample, we need to kind of have an idea of where it falls, like where could it potentially have fallen, right? And so when we know the shape of the population, or the sampling distribution in this case, then we have an idea of where our sample could have come from. And hopefully centered around the true proportion, of course, right? So large counts helps us know that it's normal, and this did meet large counts. So those are our 3 conditions: random sample, 10% rule, large counts. Always have to be met, those 3: random sample, 10%, large counts. All right, so if you look up at the top, I wrote our point estimate plus our margin of error is going to give us our confidence interval. And then margin of error, you see I have that arrow, which is our critical value times our standard deviation. Now when we start working with means, you're going to know why they call it critical value and not z-score. So margin of error says how far away from the true center are we okay being? And so that's our z-score in this case. So with proportions, your critical value will always be z. This is on the formula sheet. Margin of error, look for it, you'll see it. Point estimate plus or minus margin of error, confidence interval. So when we learned empirical rule, I told you in a normal distribution, 95% of the data will lie within 2 standard deviations of the mean. And I kind of lied to you because I was rounding. And we always round when we're working with the empirical rule, because it's just kind of an estimate. And so in this next little bit, hopefully you realized, using table A or inverse norm, that, I mean, it's really close to 2, but not quite 2. And we're going to use the more exact version of 95%, not the empirical rule one. This is the critical value. It's our Z. And they put a little star by it. You're going to see it on the test and from here on out. If the Z has a little asterisk there, it is the critical value that we're going to use. Okay, so if you look at this nasty drawing that I have over here, that I'm actually going to erase and try again. So hopefully you understood where these numbers are coming from, but if you did not, I'm going to explain it. So if we want 80% of our, hopefully 80% of our samples are going to lie in here, right? I mean, they should if it's normal. They will, okay? So we have all these samples, and we want to make sure that we're going to be catching 80% of those, okay? So that will give us our margin of error, how wide we want our confidence interval to be. And so we're going to base it on that 80% are going to just be there within a certain amount of standard deviations from the center, which is the true proportion of kisses that land flat. So in order to find that value, remember table A always reads from left to right. So if I have 80%, that means I have 10% here and 10% there. And so I can either look on table A for 0.1 or I can look for 0.9, either one. They'll both give me the same z-score. This one will give me a -1, and I just drop the negative, and this one will give me a +1. So if I capture 80% of the data, then that means I can go out as far as 1.282 standard deviations that way and 1.28 standard deviations that way. So we just ignore the negative if we do 0.1. Now, if you're doing it on your calculator, you're just going to hit second vars. And remember, we do norm CDF to usually find the probability reading left to right. So we're going to actually use inverse norm this time. And in area, we're going to put 0.1. And then you're going to leave the mean as 0 and the standard deviation as 1, just so that it's the normal. All the standard deviations are related to 1, which will give us this z-score, okay? All right, so try that in your calculator, and then you can see I did it for the rest, so go ahead and try those. 9, hopefully you calculated your margin of error correctly. We use our critical value, which is our z-score, for 95%, which is 1.96, multiply it by our standard error, which is our estimated standard deviation, and we get 0.137. Now we're creating it. We take our point estimate plus or minus our margin of error, and we get our confidence interval. So between 0.283 and 0.557, we're 95% confident that we captured that true proportion. Now I'm going to have students come up to the board and draw their confidence interval. And because they all had different p-hats, they're all going to be different distances. They're all going to be a little bit different because of sampling variability. But the more we do, the better estimate we'll have of our true p, because they're going to capture it 95% of the time, right? Okay, so if we make lots and lots of these, 95% of the time, they are going to capture the true mean. Not all of them will, as you see over here, okay? But in past year's data, it seems to be about 35%. Okay, so that is, what the heck happened to 10, 11, and 12? Oh yeah, we did those. We talked about those. Okay, great. Okay, 13. Again, pause this, try it, and then watch this. Identify the parameter of interest, U.S. adults that got enough sleep. The proportion of U.S. adults that got enough sleep. We've got to check the 3 conditions, which are normal, shape, and 10%. Check that it's normal so we can generalize about the population. We check that it's normal because that's where our sample is coming from, a sampling distribution, and we're assuming that it is normal, so we've got to check it. 10% condition allows us to sample without replacement, and all those conditions were met through either information from the problem or using the numbers to calculate it. Okay, find your critical value for 98%. So we're going to find a z-score for 98%. If you look over here, if we have 98%, we have 1% on each side. So I just did inverse norm of 0.01, and I got 2.33 as my z-score. Now, I haven't actually calculated my standard deviation, but that's how I'd do it. I'd multiply those two together and get my margin of error, add it to my point estimate, subtract it to my point estimate, and I'd have my confidence interval. But I haven't actually put that in a calculator, so I don't actually have my confidence interval. And then hopefully you are memorizing your interpretation, but we are 98% confident that we captured the true proportion of U.S. adults that get enough sleep, and it's between, again, I haven't calculated that. I apologize. All right, so let's get a little bit deeper into this. So I'm not trying to get political here, but just in general, it's kind of known that liberal media sways more towards, like, let's be really nice and help everybody and use our tax money to help those in need, right? And conservatives are more like, hey, hands off government. We will all just kind of help each other, but take care of ourselves without your involvement. And so, just kind of watching the news and watching the media recently, we can kind of see this divergence between the two parties, right? So I just wanted to investigate this a little bit, and kind of see what's going on. So immigration is a big issue, and liberals are kind of like, yeah, we got to help all these people. They're coming from these poor countries, right? And conservatives are a little bit more like, hey, but what about us, right? And I'm not saying that like conservatives are selfish or anything, just that's kind of, and I don't have really a stance either way. I'm just kind of taking this data and seeing what's going on, okay? And so, as you can see, the blue, kind of more Democrat views, they're going to show more pictures that involve feelings and emotions, and the conservative or Republican views are kind of more like, hey, look at this. Look, they're fine, right? Hands off, government. We'll help them, but hands off, okay? All right, so we're going to test some of these claims made back in 2016 and 2015, so you can look at those and just kind of see their standpoints and see where we're headed here. So I'm not trying to make political statements or sway you, just kind of helping you see when you do watch the news and they make claims, we can look at it statistically and kind of see what's going on too. So trying to put, instead of the emotion that both of these parties try to evoke, just kind of look at the facts more. That's kind of the goal of this activity. So you don't get to count all the beads, lucky you, but we looked at 150 beads and we all counted them, and we had a sample of 150 beads, and it says orange represented males and blue beads represent non-males, which actually means just children or females. So not like getting any craziness on gender there, but just, so it seems like there are more pictures of children and women. I mean, we see children in there, right? Whereas this is like, look at all these men, right? So when I say non-males, we're talking about children and women, and children being under the age of 18. So how many people were actually male? So I took data from Madrid because they do keep really good records. Now this data came from a couple of years ago though, but they really do keep good records. So I do know the true proportion, but you don't, okay? So I had the true number of orange beads and the true number of blue beads, which were women and children, blue or orange being the men. And so I do know the true proportion. The beads had that. Sorry for this long backstory, but hopefully that helps you see what we're doing here. Anyways, when we pulled out our sample, we had 72. So 72 out of 150 equals 0.48. So according to our sample, 48% of the immigrants to Madrid, to Spain actually, in this sample were male. And remember, children were in the other one. So just male 18 and older, the rest were children or women. Now, number 16, we're going to try to find a confidence interval to capture the true proportion of males that are immigrants into other countries. So we're going to construct a 95% confidence interval to estimate the proportion of immigrants who are male, as you can see in 16. Now this format, state, plan, do, conclude. If you look ahead in the notes, over here, the 4-step process. This 4-step process lines you up with the rubric that they use to grade the AP test. So I have you guys memorize this process so that you get the full points possible. So in your state, you're going to state the purpose of what you're doing. And in your state, you have to have your parameter and your confidence level. So you're just going to say, state the parameter you want to estimate and the confidence interval. So you're going to be saying, I want to find the true proportion of all immigrants that are male. And at a 95% confidence level. So that's our statement. That's what we're trying to do, okay? We want to find the true proportion with this much confidence. Now our plan is going to be our procedures, our conditions. We're planning this out. Can we really do it? So can we really create a one sample? All I did was one sample, right? Z interval. This is very important. You'll always have that unless it's a 2 sample, but it'll still be Z interval for our P, which we defined here, right? So that's what that's our plan. We're gonna create a confidence interval, but we're very specific about what type of confidence interval we're gonna do. We're gonna check our conditions, which are random. So we just say the 150, and we did beads, but they represent people, were selected randomly. We just randomly chose them. So you just state that. 10% condition you can prove. So 150 is less than 1/10 of the thousands of immigrants, right? Okay, and large counts will be 150 times 0.48, which is 72, which is greater than or equal to 10. And then 150 times 0.52, which is 78, which is also greater than or equal to 2, so it's normal. So we proved the 3 conditions that are required for this. So we planned out what we're doing. We're creating this specific type of confidence interval, and then everything's good to go. We checked our conditions, so now we're going to actually do it. Now this is really annoying, but you do write out the formula. We're going to take our point estimate, and then we're going to add or subtract our margin of error. You actually have to write that out. And then the specific formula will be a p hat plus or minus our critical z times our standard deviation. And so then we'll plug in those numbers. And then, oh gosh, sorry, 48 times 0.52 divided by 150. Okay, and that's going to be 0.48 plus or minus 0.08, and then do those calculations. And that is our confidence interval. So we stated what we're going to, like our purpose, our goal, and then we made a plan and made sure that we could actually do it, that everything was going to be okay. We did it. Now we're going to make our conclusion. We are 95% confident that the interval from 0.4 to 0.58 captures the true proportion of all immigrants in Madrid that are male. All right, read 17 real quick. So if we use a p-hat of 257 over 583, we're going to get 0.44. So the confidence interval would shift slightly lower values because our point estimate is a little bit lower. So it would shift those values a little bit lower. Now notice our sample size. Our sample size was originally 150. Now we're using 583. So if a sample size increases that much, that would significantly decrease our variability in our sampling distribution, and so that would make our interval really small. So our standard deviation would be a lot smaller there too. So I'm not going to make you watch as I write that out, but that is what would happen. Okay, and the last concept that we need to know is how are you going to know how big your sample size should be, besides that it has to be normal? What are you going to do for your sample size? All right, so we're going to use a conservative estimate for p-hat. So looking at use a conservative estimate for p-hat, how large of sample is needed. So let's go back up to 18 and read through that and see what's going on. So there's this group that wants an issue to be placed on the ballot, and it requires 20,000 valid signatures in order for that to happen. And so this group turned in their petition. They had more than enough, 24,598. But in order to pass the validity test, right, it had to have 20,000. So 81.3% of the signatures must be valid. It's way too time consuming to check all those signatures, right? To look at the signature and look up and see if that person actually exists, and see if we can find record of their signature. So way, way, way too much. So let's see if we can sample and then create a confidence interval that's where we're 95% confident that we'll catch the true proportion of valid signatures, but we want our margin of error to be within 2%. So we really so let's say it has to be 81.3%, right? Valid signatures. So we want to be within, right? So that's what we want, but we've got to be within 2% to try to capture what that true, right? So ignore that percentage for right now. Sorry, I'm getting a little bit ahead of myself. But we want our margin of error to be at most 2%. So let's kind of think about it. Margin of error. Our margin of error needs to be 0.02. Now, how do you calculate margin of error? So it's always critical value. So our critical Z times our standard deviation. And here's the thing. How the heck are we supposed to know our p-hat if we haven't even sampled yet, right? So we're first trying to decide how big our sample should be before we go and do it. So it says use a conservative estimate. So I kind of want you to think. Our z-score is 95%, so we know that that's going to be 1.96. 95%, 1.96. Now, our p-hat, we don't have. Conservative, meaning we're going to make p-hat times 1 minus p-hat as big as it can be. So we are preparing for the worst, but hoping that our p-hat is going to be the smallest standard deviation that it can be, okay? So I just want you to kind of think, what if our p-hat was 0.1? Well, then our 1 minus p-hat would be 0.9. So 0.1 times 0.9 is 0.09, okay? What if our p-hat was 0.2? Well, then our 1 minus p-hat would be 0.8, which is 0.16. So that's bigger, right? So we don't want to use 0.1 because that would give us a really, really small value here. 0.2 times 0.8 is getting bigger. Okay, so think of kind of the worst p hat that we could possibly get. What would be the very worst p hat we could get? Well, it's 0.5 times 0.5, okay? And just try numbers, just look at that. So when p hat is unknown, use p hat equals 0.5. It's going to be the worst number you could get there. So it'll, because we want it to be 2% or smaller. And so if we prepare for the worst possible scenario with our p hats, then even if the worst happens, we'll at least be 2% or smaller. Okay? Okay, so 0.02 equals 1.96 times 0.5, or times the square root of 0.5 times 0.5, because 1 minus 0.5 is 0.5, divided by n. This is how you set it up. Now you actually get to use some math in this class, right? Finally. So we're going to divide by 0.96, 1.96. We'll get a value there. I'm going to just leave it there. Then we're going to square both sides, right? So that'll get rid of our square root. So we're going to have 0.02 over 1.96 squared equal to 0.5. 0.5 times 0.5 is 0.25 over n. So I'm going to multiply both sides by n. And then I'm going to divide both sides by that. So I have n equals 0.25 divided by 0.02 over 1.96 squared, which will give me 2,401 people that I need to sample, signatures that I have to sample. Now, if it's multiple choice, you're always going to round up if that does come as a decimal, because even if we get like 0.2, we need that person to get the 2%. Now, go ahead and finish these out. If you have any questions, email me. I am going to put this page online so you can see it, but that's all that you need to learn for today. So good job. Email me. Finish this, and then I'll put the key up on Canvas.